9.8 Deformable Systems. The outline of this video is as follows. First, we will introduce the concept of deformable systems, which are systems of particles where the distances between constituent parts can change. This is a crucial distinction from the rigid objects we have often studied. Next, we will explore why the standard work kinetic energy theorem is often not valid for these systems. We will see that external work can change not only the translational kinetic energy, but also the internal energy of the system. To properly analyze these situations, we will turn to more general principles. Finally, we will apply these concepts to a detailed worked example involving two blocks connected by a spring. This example will demonstrate how to correctly use conservation of energy and the impulse-momentum theorem to understand the motion of a deformable system. Up to this point, our study of mechanics has focused on particles or rigid objects that do not change their shape. We will now introduce deformable systems, which are an important class of problems where the shape or internal configuration of a system changes during an event. A simple example is pushing off a wall while standing on a skateboard. To do this, your arms bend and then straighten. This motion changes the shape of your body, which is part of the system. This kind of deformation is very common. Your body is a deformable system whenever you run or jump. The key challenge is that because parts of the system are moving relative to each other, some of our previous tools, like the work kinetic energy theorem, are no longer sufficient. We will need a more general approach to analyze these situations. The main takeaway is that for systems that change shape, we must account for the work done by internal forces and the resulting changes in internal energy. Let us explore why the work kinetic energy theorem can fail for certain types of systems, particularly those that are deformable. A deformable system is one where internal parts can move relative to each other, changing the system's shape, like your body when you push off a wall. Consider the skateboard example again, where the system is you plus the skateboard. The external force causing you to move is the force from the wall on your hands. But while you push, your hands stay fixed against the wall. Since the point where the force is applied has zero displacement, the work done by this external force is zero. However, you and the skateboard start from rest and accelerate, meaning your kinetic energy increases. So the change in kinetic energy, delta K, is a positive number. This creates a direct conflict with the work kinetic energy theorem, which states that work equals the change in kinetic energy. Here, we have zero work, but a positive change in kinetic energy. The equation is not balanced. This shows that the standard work kinetic energy theorem is often not valid for deformable systems because it does not account for changes in internal energy. Since the work kinetic energy theorem often fails for deformable systems, we must use a different approach. We can successfully analyze these situations by applying two fundamental principles: conservation of energy and the impulse-momentum theorems. First, let us consider energy. If we define our system as the skateboarder, we can treat it as isolated in terms of energy. The equation delta K plus delta U equals 0 shows that energy is conserved. Here, delta U is the decrease in chemical potential energy stored in your body from previous meals. This stored energy is transformed by your muscles into the system's kinetic energy, delta K. Next, we apply the impulse-momentum theorem. The system is not isolated in terms of momentum because the wall exerts an external force. This theorem relates the system's change in momentum, m times delta, v, to the impulse delivered by that external force. To find the exact change in velocity, we would need to know how the force from the wall changes over time. So for deformable systems, we must apply both energy and momentum principles, carefully noting when the system is isolated for each quantity. In this example, we will analyze the motion of a system made of two blocks and a spring, when an external force is applied. This problem provides an excellent application of the impulse momentum theorem for a system's center of mass. We begin with two blocks of equal mass m, which are at rest on a frictionless, horizontal table. They are connected by a spring of negligible mass that is initially relaxed at its natural length, L. Next, a constant horizontal force, F, is applied to the left block for a short time interval, delta, t. During this interval, the left block moves a distance x1, and the spring pushes the right block, causing it to move a distance x2. After this time has passed, the external force F is removed. Our goal is to determine the resulting motion of the system's center of mass. To find the final speed of the system's center of mass, we will apply the impulse momentum theorem. This is an effective approach because a constant external force acts on the system, causing its momentum to change. The theorem states that the net external impulse equals the change in the system's total momentum. The impulse is the force F multiplied by the time interval, delta, t. The system's total mass is 2 m's, and it starts from rest. This gives us the equation, 2 times m times the final velocity of the center of mass, v cm equals F times delta t. The key challenge is that we do not know the time interval. However, because the external force is constant, the center of mass accelerates uniformly. We can therefore find the time interval by dividing the displacement of the center of mass by its average velocity. The displacement of the center of mass is the average of the two block displacements, and its average velocity is simply 1/2 of its final velocity. Substituting this expression for the time interval back into our impulse momentum equation allows us to solve for the final speed. The resulting speed of the center of mass is the square root of the quantity F times the sum x1 plus x2, all divided by 2 m's. Now, let us find the system's vibrational energy after the external force is removed. We will use the work energy theorem, which states that the net work done on a system equals its change in total energy. The total energy change can be split into two parts: the change in the center of mass kinetic energy, which we call delta kcm, and the change in the internal vibrational energy, delta E vibe. The work, W, is done by the external force F as it moves through a distance x1. It is important to remember that work is calculated using the displacement of the point where the force is applied, not the displacement of the center of mass. Since the system starts from rest, the initial energies are 0. This means the final center of mass kinetic energy plus the final vibrational energy equals the total work done, which is F times x1. We can solve for the vibrational energy by subtracting the center of mass kinetic energy from the work. After substituting the expression for the center of mass kinetic energy using the velocity we found earlier, the algebra simplifies. The final vibrational energy is F times the quantity x1 minus x2, all divided by 2. Let us summarize the essential concepts for analyzing deformable systems. A deformable system is one whose shape can change during an interaction. This change is important because it allows the system to convert its own internal potential energy, such as chemical or elastic energy, into kinetic energy. A common mistake is to apply the simple work kinetic energy theorem. This theorem is often invalid for deformable systems because the work done by external forces does not account for these internal energy conversions. Therefore, the external work alone will not equal the change in the system's total kinetic energy. The correct approach is to use two powerful and independent principles. First, we apply the law of conservation of energy, which includes changes in both kinetic and internal potential energy. Second, we use the impulse momentum theorem, which relates the net external impulse to the change in the system's total momentum. A crucial detail in the energy equation is the definition of work. The work done by an external force is calculated using the displacement of the specific point where the force is applied. It is very important not to confuse this with the displacement of the system's center of mass, as they can be different. For systems that can deform, we must use a broader energy conservation model and be precise about how work is calculated. Let us wrap up by reflecting on two key questions related to our examples. For the first question about the skateboarder, consider what happens if the system is defined as only U. The crucial thing to remember is the definition of work. Work is done when a force acts through a displacement. Ask yourself, does the point where the wall's force is applied to you, your hands, actually move? The second question probes a similar idea from the two-particle example. It asks why the work done by the external force F is calculated using the displacement x1 and not the displacement of the system's center of mass. Once again, the formal definition of work provides the answer. The displacement in the work equation is specifically the displacement of the point of application of the force. This is a critical distinction for deformable systems. Thinking through these questions will reinforce the precise definition of work and how it applies to systems that can change shape.